Um, so in the class we were talking about state assignment. And we started with this state table, and we went through the state assignment procedure. And the state assignment procedure was based on three guidelines. Guideline G1, that we have to group incoming neighbors, and G2, we want to group outgoing neighbors. So and there was a G3 that group states that have same output for same input, but this is lower priority, and this is for making the output expression simpler. And we went through the entire procedure, and I'm going to repeat it just for the sake of completion of this video, but you can what's the word? Skip this part if you attended the class and understood this part. So if we apply criteria G1, what states should be grouped together? So what are in neighbors? In neighbors are states that are who have a common next state. So for example, we start with S0. What state is S0 a next state of? So S0 is not a next state of any of the states. Then we look for S1. What states is S1 next state of? That includes S0, that includes S2, that includes S4 and S6. So here S1 is a next state for all of them. So S0, S2, S4, S6. Right? And we can continue analyzing this. Let's do this for S2. What S2 is next state for what states? Yeah. So we need to group these states together. And what does grouping mean? What does grouping mean? We'll come to that soon. So what is S2 the next state of? S2 is the next state of S0, S1, S3, and S5. And then we move on to S3. What is S3 the next state of? S3 can be found here and no one else. So S3 doesn't have more than one incoming neighbor. So S3 doesn't lead to any new groups. Then we look for S4. S4 is here and nowhere else. S4 doesn't look for any new incoming neighbors. Uh, so we look for S5. S5 is next state of S3 and S5. So we have another group here, S3 and S5. Then we look for incoming neighbors into S6. So S6 is next state here and here, which is S4 and S6. And that's it for incoming neighbor. Now we look for outgoing neighbors. Outgoing neighbors are all the states that have a common present state. So what are the common present states? So we start with common present state for S0, S1 and S2 must be grouped, and S3, S2 must be grouped, and S1, S4 must be grouped, and S5, S2 must be grouped. And S1, S6 must be grouped, and S5, S2 must be grouped. So we say this is time twice. S1, S6 must be grouped. So this one is much easier to look into, and we leave the low priority guideline for now and just try to fill next so-called state assignment map. So here we have 7 states, and 7 states is greater than 4 and less than equal to 8. So we need 2 raised to 8 is 2 raised to power 3, so we need 3 flip-flops. And let's name those 3 flip-flops Y2, Y1 and Y0. And let's draw a state assignment map, which is like a K-map, but instead of filling ones, we'll fill the state name. So here we have Y2, Y1 for these 2 columns, and Y0. This graph is just not helping. So this is here, and let's assign S0 to an arbitrary column, and then we want to make a group of S2, S4, S6. So for now, let's just label them as such. This is little arbitrary. We are trying to make as many groupings as possible by hit and trial, and we have satisfied this grouping because we can group all of these together in a K-map, and then we have these groups that occur more than once. These are because these occur more than once, these are higher priority groupings, so we group them by putting an S5 here and S1 here. So now we can group these 2 here. And then we S3 remaining, which we can put either here or here. Let's see how many groupings we were able to do. So we were able to do S3, S5, we were able to do S0, S2, we are able to do S3, S2, no. You're able to do S1, S4 now. So this is one of our state assignment. We can do it in many other ways. We can prioritize. This one for which we'll get another assignment. But let's just stick to this one. And let's create something called next. Let's go back to blue. Next state map. So in this will include X, that is the input, and then Y2 for these two columns, and Y1 for these two columns, and then we can also, so this state assignment map leads to a state encoding. We can read off the state encoding from here. So this is 0, 1, 2, 3, 4, 5, 6, 7. And we have S0, Y2, Y1, Y0. You can read off the encoding from here. So S0 is 0, 0, 1, S1 is 1, 0, 0, S2 is 0, 1, 1, S3 is 1, 1, 0, S4 is 1, 1, 1, S5 is 1, 0, 1, and S6. S5 is, sorry, 0, 1, 0, and S6 is 1, 1, 0. And we can copy this part here, and try to draw a next state map. So we have our encodings, and we can move this here and include X here. Let's say for now X equal to 0, 0, 0, 0, 0, 0. Okay. So we have an encoding of S0 as 0, 0, 1, and encoding of S1 is 1, 0, 0, and S2 has 0, 1, 1. And then when X is 0, then we get some kind of next state, and so we are focusing on this particular column. So when S0 is 0, 0, 1, let's say, let's number these. Sorry, 0, 0, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So when S0 is our present state, that is encoded as 1, we get the next state as S1. And when it is 4, then we get our next state as S3. When our encoding S2 is 3, then we get our next state as S1 again. And when we get S3 as 1, 1, 0, that is 6, then we get next state as S5, and S4 is 1, 1, 1, then we get next state as S1, and when we have S5 as 0, 1, 0, that is 2, then we get our next state as S5, and our current state is S6. S6 we have encoded as 1, 0, 1. Then we get next state as S1. And when X is not 0, when X is, instead of being 0, it is just 1. Then we get a different kind of state assignment. So then we are focusing on this part of the column, this column. And when our present state is S0, that is 1, 0, 0, 1, that is 9, then our next state is S2. When it is 12, S1, then our next state is S2 again. When it is 1, 0, 0, 1, 0, 1, 1, that is 11, then we get S4. When S3 is 1, 1, 0, that's 14. S3 is, next state is S2. And when S4 is our current state, that is for 15, and our next state is S6. And when our current state is 1, 0, 1, 0, that is 10. Then our next state is S2 again. And when our current state is 1, 0, 1, 1, that is 13. Um, then our next state is S6. Okay. We got the next state map, and you'll see big groups of same state here. For example, here is a group of 4 S1s, and if you go back to the assignment map, the group that we created, so we chose this group of 4 to be grouped together in the state assignment map here, right? And this group are all incoming neighbors of S1, and you get a group of 4 S1s here. And if you see this group of 2 S5s, so these 2 S5 came here because S5 is a neighbor of S3 and is a next state of S3 and S5, which corresponds to 2 and 6 respectively. And this came, so this is here because we grouped S3 and S5 together, and this is what we included here. So this is the so now we can appreciate why guideline 1 is important, right? It creates these groups of the same state because they are the common next state. So in the next states map, these states appear closer together. But why do we need guideline 2, which is about out neighbors? Or common present state, right? Why do we need this? So by putting the guideline 2 or out neighbors, so the major guideline 2 we focused on was S2 and S5 and S1 and S6. So when we put S2 and S5 together, right, or we group them closely together, then their encoding for S1 it's 0, 1, 1, and for S5 it's 0, 1, 0. So that differs only by 1 bit. And for S1 and S6, our encoding is 101 for S6, and for S1 it's 100. So it differs only by 1 bit. So you can split this next state map into 3 K maps. Let's build them one by one. So here we have box divided by half, 16 cells, and we have X as these 2 columns, small y2 as these 2 columns, y1 as these 2 columns, y0 as these 2 columns, right? And our next state is made up of 3 blocks. So y1, y2, y3. So let's copy this over here and paste again. Okay, so we have our eraser. Okay, so this is, so each next state is also a 3-bit encoding, and that is y2, y1, y0. So what we can do, zoom out a little bit here. So here we have D, 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 and S3. What is the encoding of S3? 1, 1, 0. So 1 for capital Y2, 1 for capital Y1, and 0 for capital Y0. And similarly, we can split this next state map into 3 state maps by expanding on the encoding of S1. So S1 is 1, 0, 0, so it's 1, 0, 0. Since we have 4 S1s, we can just copy these and move on to the next one. S5 has the encoding of 0, 1, 0. Okay, and then we have encoding S2 of 0, 1, 1, 0, 1, 1, D, D, don't care, and we have 0, 1, 1. Then we have S6, and 6 has encoding of 1, 0, 1, 1, 0, 1, and S2 again, copying wherever S2 was common. S4 is 1, 1, 1. So the guideline 2 doesn't create common groups across all 3 K-maps. So guideline 1 creates common groups across all 3 K-maps, but guideline 2 creates groups in 2 of the K-maps. So here you have S2 and S5. So if you focus on wherever S2 and S5 were there as next states, they were always adjacent to each other. So example, here S2 and S5 are adjacent to each other. So because S2 and S5 differ only by 1 bit, wherever they don't differ creates a big group. So here the adjacency of S2 and S5 created these 2 bit groups, and because they differed in 1 bit, so that doesn't happen here. Similarly, S1 and S6 are close here, and because of that these 2 big groups are created. So now we can read off our expressions for next state, and if we are doing a D flip-flop, then that would be D2 is Y2 and Y2 can be written in terms of groups of 4. We explicitly focused on these 2 groups, these 3 groups, but we can either do all 1s or all 0s. So this one looks pretty lonely. We can group it together with this one, and call it y1, y0 plus we can group these together. Can't be expanded to even a bigger size, and we can call that one bar x bar. We are just left with this one, which is y2, y0, and then we can write d1, which is just y1. And here we are looking at this group of one. Either we can group these. This is a big group of ones here, group of 8, and that is just y0 bar plus x y2 bar. For this one, and for y0 we just get x. So this is these are our expressions for if we are making circuits using D flip-flops. So we'll need 3 D flip-flops, and here we can start by making start around D flip-flops here, make all of our D flip-flops, and so the outputs of our D flip-flops will loop back as present states, which are small y2, small y1, and small y0, and the output, there is one input x, and here we want to make 3 AND gate and 1 OR gate circuit. And here first one is y1, y0, and you can loop it back from here, right here, but to avoid congestion, I'm just labeling them. You get y1 bar, x bar, and y2, y0, right? And then for D1, you have y1 bar going into this, and a single AND gate taking in x and y2 bar, and this one you just get an input x. So that will give you the state part of the circuit, and then we also have this Z part of the circuit, which is again a K-map. Let's make it using straight lines. X again, y2 again, y1 and y0, and we have this encoding that we are going to copy here, and this output table that we are going to copy here. Now we can write let's number the minterms. So for 001 we have 0, for state 1 which is 4 we have 0. Basically for x equal to 0 we have all zeros, one don't here, and except the S5 which corresponds to 2, that is 1, but otherwise everything else is 0. And for x equal to 1 we have S6, whose encoding is 101, that is 5 plus 8, 13, so that makes this 1, 1 and rest of them 0. So there is no grouping possible in terms of 1, but we can write these two ones explicitly by saying x y2 y1 bar y0 plus x bar y2 bar y1 y0 bar. And so this circuit Z would require 2 AND gates and OR gate, and it will require 4 inputs in each of the AND gates: X, Y2, Y1 bar, and Y0, and X1 bar, Y2 Okay, and you can connect those wires if you want to, but that's the basic idea.